Okay, so this is the these are the exam 3 review slides, stuff like that for fall 2016, stuff like that. So this is again, like always, these are the free answer parts. Okay, stuff like that. So stuff like that. So one of the questions is going to be going from a regular molecule into a Newman projection. Okay, and so for here, you've got propane, right? So with that, so it doesn't really matter which. So you're going to want to look down the carbon-carbon bond. It doesn't matter which set you do. So let's let's do this. Let's do these two, and you got to figure out which one's the front, which one's the back. Again, it doesn't matter. I'll figure out which you're looking at. So with that, so let's say that's the front, and then let's say that's the back. This is the back carbon. Okay, so the front carbon, right? So with that, and so first thing to do is don't even worry about the lowest energy state. Just draw the molecule. Okay, and so we're going to want it like this, right? So we're going to have the three things hanging off the front carbon here. So what do we have? We have these two hydrogens. So just put them somewhere. Okay, and the and there's going to be this methyl group here. So there. Okay, so remember, we're looking between this carbon-carbon bond here, and so like that. So this is the front one. The back one, we won't be able to see the carbon. We can see the things coming off of it. So for here, we're going to have hydrogens. The three hydrogens coming off of here. Now the lowest energy state is going to be staggered. Okay, so like that. So this is the staggered form. So like that, where the ones in the back are halfway in between the two. Eclipse isn't going to work. That's high energy. But for this one, we're fine like this. Now, if you had non-hydrogens on the back, a large group on the back, you're going to want to get that group as far away as possible. So let's say you had a chlorine hanging off of here instead of that one of these hydrogens. You're not going to want to have the chlorine here because you're going to have what's called a Gaussian interaction. Okay, so what you actually want to do is rotate that back one around so that it's actually the 180 degrees from the big group in the front. So that's what's called the anti-configuration. For this one, it's not the big of a deal. But if you had groups hanging off of the front and the back, you're going to want to get the lowest energy state. You're going to want it staggered, but you want to get those big groups as far away from each other as possible. So for here, this is just a regular staggered is fine. If there was more than that group, you'd want the anti-form. Okay. Something like that. So if you wanted the highest, let's say you wanted the highest energy, okay, what you'd want to do is you'd want to have it into an eclipsed form, okay, and so you can say hold that front one back, like that, and so to do the eclipse, you just sort of show, do the best you can on the drawing. So you're going to want to get the ones directly on top of the ones in front. And again, the highest energy, so this is the lowest, the highest is going to be where the big things are eclipsing each other. So again, if you had a chlorine hanging off the back carbon, you'd want those big groups eclipsing each other. That would be the highest state. But for this one, that's fine. Now, is the pair of molecules constitutional conformational isomers? So for this one, remember they have to have the same formula. Constitutional isomers means that they're going to have a different name. Conformational isomers, the two are going to have the same name. Okay, stuff like that. So they've been rotated. Okay, so the constitutional is going to have a different name. So we go through those 4 steps that we normally go through to name the molecule, and if at any point we see a difference between the two, then we go in and we say, oh, we're done. The constitutional isomers. So here we go. So first things first, we got to find the longest chain. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right. So don't forget we can do it on the side chains too. So 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So it doesn't matter which one you get, but it's going to be C10. Right. So with that, so for here, right. Well, we can go through here. It doesn't matter that it's all wiggly like this. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? 1, 2, 3, 4, 5. Yep, so let's say it's this. Okay, well, the main chains are the same length, so that's good. Stuff like that. And so what do we have for side chains? Well, we have an ethyl group and an ethyl group. Well, okay. that makes them the same. So now we have to do the numbering, right? And so the numbering, right? Remember, we're going to want that lowest number set. And so the side chain's at this end, so the number sets could probably going to start here. So 1, 2, 3. So it's hanging off of carbon 3. Here, the side chain is closest to this end, so it's going to be 1, 2, 3. Okay, so this is going to be 3 ethyl decane. Okay, and this is going to be 3 ethyl decane. Right? They have the same name, so they're going to be conformational isomers. Okay, so but if this was say 4 ethyl decane, or it would be, or 5 ethyl decane, they'd be constitutional isomers. But they have the exact same name, so they're conformational isomers. Okay, so for degree of unsaturation, okay, I'm going to give you a formula like this. I'm going to give you the equation just like this. It's not going to be on the equation sheet. You just need to know what this are, what these. I'm not going to give you the key, right? So it's going to be 2 times the number of carbons plus 2. This is a constant, okay? Plus the number of nitrogen minus the number of halides, and so X would equal to the total number of these fluorines, bromines, chlorines, and iodines. Okay, they're just going right down. They're just going. Ooh, you can't see that. Sorry about that. Fluorines, bromines, chlorines, and iodines. Right. So we're going to go right down that periodic table, which I'll give you the periodic table. Any of those in there. Okay. If there's 2 bromines and a fluorine, right, that would be 3. Okay. So by that, there's a fluorine, a bromine, a chlorine, and an iodine. Right. That would equal 4. Okay. So it's the total number of that minus the number of hydrogens. Okay, so by that, so for here it would be 2 times 4 plus 2, right? That's just a constant. Right? There's no nitrogens. There's 2 halides because of the 2 bromines, so that's 2. Minus the number of hydrogens, which is 6. All that divided by 2. And notice that we didn't use that oxygen. We don't need it. Don't stick it in there. It's not part of the equation. So like that. So here we go. So 8, 10 minus 8. 2, so it's 2 over 2, and so it's 1. That's fine. It means that there's either a double bond somewhere or there's a ring. All I need is this number. 0 is fine. Stuff like that. That just means there's no double bonds, there's no pi bonds, there's no rings. Okay, 0 is fine. A fraction, not so good, right? So if you get 1.5, that means that there's something wrong. If you get a negative number, there's something wrong. Stuff like that. You need to go back. But you want a positive integer, well, 0 or above integer, something like that. So that's fine. That's all you're gonna need. I just need to know that number. Okay. So here we go. So there will be a portion where we draw constitutional isomers. Okay. So with that, but this is how it's going to be. I'm just going to have you draw three different ones. Okay. That have the formula like this and contain an alcohol group. So you're going to need to be able to. So you want to review your functional groups. Okay, so an alcohol, remember, is just it's an OH hanging off of just a regular carbon. Okay, and so here, okay, so the first thing you're going to want to do is you're going to take a look at this formula. Okay, just do a quick DOU check. Okay, so with that to make sure there's not going to be a ring or a pi bond in there. Okay, so it's 2 times 4 plus 2. Don't forget the plus 2. There aren't any nitrogens, there aren't any halides, but there are 10 hydrogens. Okay, so 2. So it's 10 minus 10 over 2. So it ends up being 0. Okay, so there aren't any rings, there aren't any pi bonds. Now, if there were, say you could start off with say you could do like a 4-membered ring, right? A square. Or you could do a triangle with a methyl group hanging off of it. Okay, but usually for things like this, usually the easiest thing to do is to start with the longest main chain. But here we don't have any, so we're fine. So we're just going to start off with 4 carbons in a row. Okay, and then we can say put the OH here. Okay, that'd be okay. Start with 4 chains in a row. We can just keep going down, right? So OH there. OH there. Okay, or OH there. Okay. The only problem is, if you notice, these two, you could say, oh, well, those are the 4, right? We only need 3, so we're good. The problem is these two are the exact same molecule. If you just take this one and just flip it over, it's that one. Okay, so they're the same molecule, so we don't need that one. pick one. The same goes with these. Okay, this and these two molecules are the same. If you take this one and just flip it over, it turns into that. Okay, so we don't need that. Okay, so we've really only drawn two molecules. Okay, so when you get to this point, right, so you got to make sure, if you could do it systematically, but you have to go back and take a look and make sure that you aren't duplicating things. Okay, so you start off with the largest main chain, and then you cut it out. So what you can do is you can lop off one of the carbons and then stick it on here as a methyl group. So the problem, but you do have to be careful, right? Because you can say, okay, well, there's my 3-carbon chain. If I put the methyl group there, okay, the problem is the main chain is right there, right? And you've just redrawn this so that just kinked down, okay? And so this is the same as that chain. So what you really need to do is you really need to have it like this, okay? So you have a main chain of 1, 2, 3, or 1, 2, 3, or 1, 2, 3, like that. Now you can come in and you can put in your OHs, okay? You see them here, here, here. Like that, okay? Now, the only problem is, okay, so now you gotta look for duplicates. The only thing is, these three, as it turns out, are exactly the same, okay? And stuff like that. And so, let me see if I can show you this. Get out here, right, stuff like that. So if I put the OH here, right? Now, so that's this molecule. If I just flip it over, it turns into that one. Okay, if I rotate it, it turns into that one. Okay, and so these three are actually all the same, so we don't need these. Okay, stuff like that. Now, in order to make this one, though, I have to take off the hydroxyl and move it here. I can't rotate it, right? So okay, so that's the fourth one. So really, there's only in total 4. I'd only want you to draw 3 of them, but there's really only 4. But this is a good exercise to go through, because if you want to be systematic about it, you got to make sure that you aren't duplicating something. If you were to just draw this one, this one, this one, I'd say, nope, that's wrong. You really only drew me 2. So you get partial credit, but you wouldn't get full credit for it. So be careful. Okay, now cis and trans, right? So for cis, all we're talking about is up and down. Okay, so cis, they're either both going up or both going down, right? Trans, you got one up, one down. Okay, so for the Haworth projection here, right, this chlorine is going up, this chlorine is going up. Okay, so this one's cis. Okay, now for here, right, this one is pointed down, right, this one's pointed up, right, so that's trans. There you go. Now you got to remember, right, so if it was, let's say if it was here, right, again, it would be pointed up, right, here, up and up, like that. So this would be, if there was these two, then it'd be cis. Okay, but don't overthink it. So okay. Okay, now for the chiral centers, okay, so with this, so what you're going to do, so if I give you a molecule like this, the first thing to do is to fill in the hydrogens, okay, so, you can put in your dots, okay. Okay, so for this carbon here, we've got 1 bond shown, so that means the other 3 bonds that the carbon needs are hydrogens, right, because remember with the skeletal structure, we don't need to show them. Okay, for this one here, right, 1, 2, 3 bonds are shown. So that means one of these is a hydrogen. Here, 2 bonds are shown, so so it has 2 hydrogens on it. Same thing here. Okay, this one here, right? 1, 2, 3 bonds are shown, so that means the 4th one is a hydrogen. Here, 2 bonds are shown, so it's a CH2. 1 bond is shown, so coming off from that dot, so it's a CH3. Now, in order for it to be a chiral center, you need 4 different things hanging off of it. Okay, so for here, right, there's 3 hydrogens. Well, all 3 hydrogens are the same, so it can't be here. Here, it might be. Okay, but here, CH2, right, it's got two hydrogens, can't be a chiral center. This one can't be, that one and that one. Okay, this has 2 hydrogens, has 3 hydrogens. Well, so if you put in the hydrogens, you can quickly eliminate all the other things it can't be. Now, it doesn't necessarily guarantee that these are, but you can at least eliminate these other ones really quickly. Okay, so for here, what you're going to want to do is you're going to start where you think the chiral center is, and then look at the four groups hanging off of it. So you have a nitrogen, a hydrogen, a CH3, and a CH2. Okay. Well, those are four different things: CH3, CH2, H, and a nitrogen in a 2 group. Well, those are all different. So that means that there's 4 things. So there's a chiral center there. Now for this one, right? So this is the other potential one, right? We have a hydrogen and a chlorine. Well, those are obviously different. Well, now here we got CH2, CH2. Well, okay, so it's a tie. But what we do is we go to the end of the chain and see if there's a difference, right? So even though there's a tie here, what we do is we come out one further, and so now we compare CH2 to CH3. Well, there's a difference here and here, right? So that means this side is different from that side, which obviously it is. Yeah, I was going to say because this has all this other stuff. So that means that this is a chiral center. So there's 2. There's one here, and then there's one there. So those are your chiral centers. Okay, so for optical rotation, so this is the one where you've shown in class, right? So you're going to get this is the specific rotation. This is the rotation this is the measured rotation, specific rotation, concentration, wave, path length. Okay, so for here, right? So gives a rotation of 25 degrees. Okay, so that's 25 here. Okay, the concentration I said was 0.035 molar. Okay, and then the path length was 1 decimeter. So this is the one. I'm going to give you 3, right? So like that. So I'm going to give you 3 of these, and you got to give me that 4th one. Okay. So like that. So it ends up being, right, 25 equals path length times 0.035 times 1, right? So your specific rotation ends up being 25 over 0.35, 035, which I believe is 714 degrees per, this is molar and this is decimeter, per molar per decimeter. Okay, so there. I'm going to give you 3 of those. You got to give me the 7. Now, notice that the temperature and the wavelength don't come into play in these calculations. If I give them to you, they're just raw red herrings, right? You don't have to worry about them. So like that. So, but again, I'm going to give you this equation. It looks just like this on the equation sheet. You're just going to need to know how to use it. Okay. Now, for R and S, okay, this is where a good model kit can help. Okay, so you're going to have a big arrow pointing to where the chiral center is of interest. Okay, so you look at, so here's our carbon, all right, chiral carbon, right? We can look at the four atoms attached, right? So you're looking at at a hydrogen, a chlorine, a carbon, and a carbon. Okay, so the heaviest one is going to be the chlorine. The next heaviest is going to be one of these carbons. Okay, but we know the hydrogen is going to be last. Okay, so there we go. Okay, so now for here, right? So this is a CH2 and a CH2. Okay, so they're carbons, right? So we're going to look at the bonds because it's a tie because they're both carbons, right? So it's 2 carbon-carbon bonds versus and 2 carbon hydrogens. Here, right? We're looking at 2 carbon-carbon bonds, 2 carbon-hydrogen bonds. Well, the heaviest bonds are carbon-carbon, and there's 2 of them. So that's a tie. So then you look at the quantity. Well, then there's 2 of them. Well, okay, so it's a tie. So when we get a tie like this, we go out one further, right? So now we're looking at that one versus that one. Okay, so now here, right? There's 3 bonds are shown, so there's a hydrogen here. 2 bonds are shown, so this is a CH2. Okay, so this ends up being, right? It has 2 carbon-carbon, a carbon-chlorine. Carbon-chlorine, and a carbon-hydrogen. Here it's 2 carbon-carbon and 2 carbon-hydrogen. So now we're looking at carbon-chlorine versus carbon-carbon, and since this is heavier, that's the first thing we look at. This is heavier, so this gets the priority. Okay, as soon as you start radiating out, as soon as you find a difference, you stop. Okay, so we found a difference. It's here, so we check out those. That's a tie. We go here. Then that's we find a difference, so we stop. So that means that this is a higher priority than this. Okay, this side is a higher priority than this side. Didn't matter if you had like massive amounts of groups over here. You found the difference there. You're done. Okay, so let's rewrite these with just the numbers. Okay, so now here, okay, so the 4 is going that way, okay, and so the 1 is up here, the 2 is behind, and the 3 is over here, okay, so if I were to, so your thumbs are going to have to point this way, okay, and so your fingers are going to want to point, up, fingertips start for 1, so if you're going to try with your right hand, you go 1 to 2, because the 2 is behind, so 1 to 2. That's not going to work. But if I started with my left hand, I start the 1 over here, and I can sweep to 2 over here, and then 3 up here. I can sweep 1 to 2 to 3. Start your fingertips at 1 with your thumb pointed where your 4 is pointing. 1 to 2 to 3. Okay. The other way that you can do it, if you're doing the steering wheel method, is you say, okay, this is 4, okay, 1 is out here, the blue is 2, the green is 3. If I rotate this, okay, to get 4 behind, it ends up looking like this. So the 1 is over here, so this rotates over here, the 2 rotates forward, and the 3 rotates over there, right? So since I'm going counterclockwise, it's S. Which is, and again, if we used our right hand when we were doing the hand method, right? So that makes it S as well. So if it was clockwise, it'd be R. If we swept with our right hand, it would be R. Okay, now for here, what we want is we're going to look at this side, and then we're going to look at this side, right? Because first thing we're going to do is draw these things down the middle, so we're going to slice it in half. So we're looking at the carbon on this side of the double bond, and then we're looking at the carbon on this side of the double bond. Okay, so now here we're comparing the hydrogen versus the carbon, right? So this is going to be a higher priority, high, and this is a low priority, okay, because carbon's heavier than hydrogen. Now for here, we're going to, okay, so that we've done this side, so now we're looking on this side, right? So here, it's carbon versus carbon, right? So because we compare that versus that, right? So but since it's a tie, we look at the bond. So here, you're looking at 1 carbon-carbon bond, 3 carbon-hydrogen. Here, you're looking at, right, 2 carbon-carbon bonds, right? Because this is a CH2, right? 2 bonds shown, 2 carbon-carbon bonds shown, so that means the other 2 have to be carbon-hydrogen. Carbon-hydrogen, carbon-hydrogen, that's a tie there, but this one has 2 versus 1, so that means that this is the high, this is the low. Okay, then you take your hands off, right? So we're looking at where the highs are. The highs are on the same side, right? So at that, so it ends up being Z. Okay? If the high was up here and the high was down here, then there would be an E. But here they're on the same side, so it's Z. Okay, so last one. Okay, so the molecule here, I'm going to give you a molecule like this, and what I want you to do is I want you to add wedges and dashes to the chiral centers, and then to make it meso, and then show me where the plane of symmetry is here. So for here, the potential chiral centers are here and here. Okay, and so what we can do. Okay, so you draw. So let's say you add a wedge here and a wedge here. Put these on a wedge, and then there'd be a nice plane of symmetry that went right through there. That's all I'm asking. Is you got to make these meso by adding wedges and dashes, and then show me where the plane of symmetry is. Okay, so if this was a wedge and that's a dash, right? You break that. That would not. One would be pointed up, one would be pointed down. There'd be no plane of symmetry. If you had them both on a dash, that'd be perfectly fine too. There would be a plane of symmetry going right through there. It's pretty easy, stuff like that. So. Okay. Good luck.